Thank you so much. So our next presenter, our next keynote speaker is Dr. Wenjin Meng, also the scientific co-investigator at SEAM. So Dr. Meng, we are here to listen to your speech. Thank you.
Yeah, good morning, everyone. Can you hear me?
Yes, we also can see your...
Can you see my screen?
Yeah, everything
is
great.
Great. So let me start. My assignment today was talk to you and give an overview about SIM research. And this is, of course, a little different task in that I am truly now speaking to the choir, because you are the body who has carried out the bulk of SIM research. So I thought what I will try to do today is actually to maybe stop you for a minute from staring at the ground, busy trying to discover delicious yet undiscovered truffles, and lift your head and appreciate the beauty of the forest that we are in. So the first point I want to make is that the SIM research, and also my task is also a little bit easier because following Professor Ramachandran, I am actually preaching to the nerdy choir, so I can actually afford to be a little more nerdy. So to begin, the SIM research is really consistent with the State of Louisiana Science and Technology Plan, which identified first material science as one of the core enabling disciplines, and advanced manufacturing and materials as one of the target growth in industries. So what SIM really wanted to do overall is to lead this state in advanced manufacturing and materials research. And hopefully all of you by now would know that SIM research is organized into two science and technology thrusts. STT1 is on multi-scale metal forming, and STT2 is on laser-based 3D printing. So for STT1, I think it's a little bit easier to focus in that what we're really doing is we're taking well-established large-scale manufacturing processes, such as the video shows here, using reverse extrusion to make a scuba diving tank. Scale that down so that now the characteristic length scale goes from maybe centimeters and larger to sub-millimeters and the micron scale. So that many different kinds of metal-based structures at the micro or the mesoscopic scales can be made with potentially different applications: heat exchange, surgical devices, heat transfer, so on and so forth. So the key point that I want to remind everyone is what are the scientific issues each STT tries to confront, face, and solve. So for STT1, I can perhaps put that simply as increase our understanding to small-scale plasticity problems and our understanding to mechanical response of solid-solid interfaces. More specifically, we're talking about understanding the how and the why materials exhibit different kinds of mechanical size effect. One specifically is that as the characteristic dimension of deformation approach a regime where the response has a strong dependence on the length scale itself. The second type of size effect is that when the characteristic dimension of deformation approaches the microstructural length scale of the material being deformed. For example, as the deformation dimension approaches the average grain size of the materials. Both types of size effect have been dealt with, and I would say made some progress of in STT1 research. The third part is to first understand and then hopefully to engineer mechanical response of solid-solid interfaces. For example, interfacial strength, interfacial toughness. And so these have significant applications to, for example, how you would fabricate and utilize forming tools at different length scales. So for STT2, the objectives are perhaps a little more diverse in that the team really starts out by either acquiring commercial capabilities for laser-based 3D printing, or as shown in the center, by actually building custom laser-based 3D printing capabilities. And on the right, in the process, making different kinds of 3D printed materials, characterize them in terms of their structure, their performance. And at the same time, conduct a very different and very broad array of simulations. For example, shown here, using CFD and finite element analysis to model the dynamics of a melt pool when laser beam hits the powder bed. And as shown here, again, using simulation methods, combined molecular dynamics and phase field simulations to address the question of, after the laser melts a part of the founding material, how would resolidification progress and form the microstructures? So here again, the scientific issues that STT2 faces are more widely spread and diverse. A list here shows that you need to understand the laser interaction with the powder feedstock. You need to understand something about the melt pool dynamics, and then perhaps more impactful to the performance of the 3D printed parts, you need to understand the process of resolidification. How does that influence the microstructure evolution, and how do you finally correlate the microstructure in the printed parts to its mechanical performance in terms of strength, ductility, fatigue life, so on and so forth. So even though STT1 and STT2 focus on seemingly quite different topics, they really face common scientific challenges and barriers. For example, the common challenges you can think about is that the two classes of problems both are multiple length scale in nature and multiple time scale in nature. We're talking about plasticity problems that goes from the micron scale to the millimeter scale and beyond. And we're talking about interfacial phenomena, say between the metal and the ceramic, that's really atomic in scale, but then has significant interactions with plasticity events that goes way beyond the atomic scale. So for the laser case, you're really talking about laser-induced melting on the microsecond and less, and going into solidification that goes from microseconds to milliseconds to seconds to microstructure development that goes in the time domain of hours. So again, it is these multiple lengths and time scales and the presence of surfaces and interfaces in the 3D printed case in terms of their layer by layer build nature. They have a multitude of interfaces. So these are the common challenges. To deal with the common challenges, we did devise some common approaches. Going from, we want to take advantage of shared computational facilities and the building up of multi-scale modeling and simulation expertise. I know that many of you who are going to present today are doing work exactly in that area. You're actually doing different kinds of physics-based modeling as well as high-performance computing. And then we want to take advantage of shared experimental facilities and fabrication facilities. Again, we want to build up the resources and expertise for material synthesis, characterization, and testing. As shown here, through the SIM program, we have really built up a significant collection of these experimental resources and concatenated them in the so-called core user facilities. So from chemical analysis with X-ray photoelectron spectroscopy, different kinds of electron and ion beam microscopy, to laser-based 3D printing, electrical discharge machining, to different kinds of vacuum and plasma processing. So once we have these shared computational and experimental resources and expertise, the common approach is actually to follow the so-called make, measure, model, and validate type of approach, which is the core of what's called integrated computational materials engineering. So with these, whoops, sorry. So with these, what we're really trying to do is to build up our critical experimental infrastructure and critical expertise for physics-based multi-scale modeling and simulation. We want to also build a strong multidisciplinary and multi-institutional R&D teams. Many of your talks, I know this morning, reflects that collaboration. And coupled with a statewide education and outreach program, the overall goal of the consortium is to achieve sustained excellence in manufacturing and materials research and development. So just to show what we have done, I think over the past several years when the SIM program is in the running, we have really built up facilities as well as a certain degree of expertise in terms of materials characterization across length scales. From the centimeter scale, looking at the gross defects using neutron imaging, small scale examination with X-ray computed tomography, to say examine materials in detail at the 100 micron cube length scale with so-called 3D slice and view, which will come online this fall, to TEM and scanning transmission microscope imaging and spectroscopy. So this array of characterization techniques would really yield detailed information about material structure and chemistry from the 1 centimeter scale down to the 1 angstrom scale. And then we have really also built up a significant amount of resources and testing expertise, testing the mechanical testing, again, across multiple length scales, from nano indentation to micropillar testing to different kinds of mechanical testing at mesoscopic scales, say 100 micron to 1000 micron length scale, to the millimeter scale and beyond. And we have also demonstrated that there is power in combining detailed experimentation with across the length scale physics-based modeling and simulations, starting from density functional theory, which deals with the atomic scale, to molecular dynamics, dislocation dynamics, then to the larger length scale of crystal plasticity, finite element, and continuum level strain gradient plasticity, finite element analysis. So it is this combination of detailed experimentation and cutting edge experimental techniques with cutting edge physics-based simulations across length scales that I would state gives us the foundation for building and sustaining a cutting edge manufacturing and materials research program. So to show some evidence of success in this strategy, many of you may have known already that NSF awarded the state of Louisiana another $20 million for the next 5 years to establish the Louisiana Materials Design Alliance. Here, the stated goal is to actually transform advanced manufacturing to smart manufacturing by combining experimentation and physics-based simulations with data analytics and machine learning. So I will use that to conclude my part of the presentation. My suggestion to you is twofold. One, I would say as students and postdocs, I would want you to hone up your own expertise portfolio. If you're doing experiments, then really work hard to actually understand the experiments that you do, hone up your portfolio of experimentation skills, and try to really do clean and incisive experiments. If you're doing simulations, really master the physics behind the simulation tools and be able to use your simulation tools to address physical problems. And I would say that one thing I have learned personally through executing this research, combining experimentation with simulation, is that this combination is really powerful and will, I think, become even more powerful as the computational capabilities progress over time. And good luck to your own presentations. That concludes my speech today.
Okay. Thank you, Dr. Meng. So we are waiting for any comments or questions. If anybody has one. Okay. I think there are no questions or comments.